Hello everyone, we are doing the lab 6 wind sensor. So the starting point is from this Dropbox to where Nestor is sitting. So what we're going to do is having Alex, the assistant, to do the video camera, and I will be walking in a steady pace, and he will also use the camera to record the angle. So let's hand it to Alex. It's recording now. So let's start our first trial. So this is what's it called, Alex?
Protractor.
Protractor, and this is our simple wind sensor we grabbed from Professor Trivat's CAD drawing. So how does this thing work is when we walk, there will be a simple flow, and that will push the sensor going backward, and we will record the angle. And using that angle, we will do the further analysis when we go back on. Are you ready? Let's do one start.
Okay.
Okay, so I'll be walking. Watch out for the Dropbox.
Yep. So start here.
Okay, start. 3. You can start.
Okay. 3, 2, 1, go.
So see, you can see a slight angle right now because there's a flow drag the sensor to going backward, and that angle is something we try to take measure at. And later on, we might use the longboard to reach an even more steadier for velocity. Stop. Okay, so that's good. And we will do one more. Are you still recording?
Yep.
Okay. So this is Alex longboard. It's part of our tool as well. Just full credit. And that's Alex. That's Nestor, one of my other group members. He's doing the data entry and the analysis. Just go back. No, it's just. Woo. Okay, Alex. All right. So I will probably start from the back a bit just for inertia, and Alex, you can start measuring from there.
Okay.
Let me know when you're ready, so we can take one.
All right. 3, 2, 1, go.
Okay. So wow.
And stop.
Okay, cool. I think that's it for our experiment part, and after this I will get the data from Nestor and start doing analysis. Thank you for listening. I will see you soon. This is Ray Hao again, and I have my assistant Alex Yao recording the video, and Nestor Barkar doing the data analysis. So during this continuation of the earlier video, we will be doing some technical analysis of the wind sensor, how it works from a fluid dynamic perspective. So let's go into the paper. Okay, so what we have here right now is a simple wind sensor. Yeah, fine. Are you able to see?
Yep.
Okay, so this is a 3D drawing of the wind sensor, and when a person walking that way, there will be relative velocity going backwards. So that will give us an angle. Let's call it alpha. And in the diagram below, here is a free body diagram of the wind sensor. So there will be a F tension which pulling the sensor backward and keep it attached. Also, for the Fg, it will be equal to the force of tension time. This will be sine alpha. This will be the gravity, and for the drag, it would be F tension time cosine alpha. And to get the relationship between them two, it will be Ft over Fg, which equals tangent alpha. Also, after this step, we also know from the thermodynamic book, the combining drags. It involves the drag of the surface and the drag of the pressure drag. So for the pressure drag, which is dominating in this case, it will be half rho u square CD, surface of the drag, coefficient of drag, and the surface of the drag, equals mg tangent alpha And from this equation, you are able to calculate tan alpha equals half rho u square CD alpha over mg tangents minus 1. So with this formula, you are able to get the angle of the drag, and this is essentially how the wind sensor works. And that's it. So the application of this formula could be airplanes, some sort of wing applications, especially in aerodynamics. And that's it. Hope you enjoyed the video. Hello everyone. You have seen how the lab is conducted and the FBD of the wind sensor from the previous video. Now we will go into source of error, fundamental principles, as well as observation and findings. So the first source of error in this lab is the protractor angle reading. It was done by aligning a camera to the protractor and measure the angle. This will bring the source of error into the lab. And second error is the constant walking speed of human. We are unable to achieve this very accurately. We are acknowledge of these two sources of errors, and we will take them into consideration when doing the analysis. Now let's go into the underlying principles. So here it comes, the underlying principle. Force of drag equals pressure times area times drag coefficient. And for the pressure, we will go into deeper using the Bernoulli's equation and transfer that into an energy equation. So the left side of pressure before hitting the wall is 0, so we cancel that out. And after that, we have a stagnation pressure, and Z1 equals Z2, so it cancels out. And in the end, we got the pressure at point 2 equals rho v1 square over 2. We know the air density of the air as well as the velocity of people walking, so we are able to calculate the pressure. And this is the diagram showing the same thing as the formula. The second item is area. Area equals the vertical distance in between and the width. And the drag coefficient is something we can calculate. In our experiment, we get a value around 3.1. And now let's go into the observation and summary. So during the lab, we found like when people walk faster, as we introduce a greater angle of tilt. So this is corresponding to the pressure. As people walking faster, there's a greater pressure which will push the sensor more on the right. And the second finding observation we found is in the book, the drag coefficient for flat surface is 2.5, but we have calculated 3.1. We suspect this is from the source of error. That's all for lab 6. Hope you have found something useful in here. Thank you very much for listening.